So today in class, we took a look at developing possible shortcuts to determining derivatives. And we used first principles to figure these out. So the derivative of polynomial functions can be done quite simply in that if your function is x squared, you're going to take your exponent value and bring it down in front and then reduce the exponent by 1. So x squared would become 2x. A lot simpler than first principles. And then x cubed, again the 3 comes down in the front, becoming 3x, and then you reduce the exponent value by 1, so you get 3x squared. So 4x squared now, if you have a coefficient, you're going to multiply the coefficient by the exponent, getting 8, and then you reduce the exponent by 1, and again you get 8x. So written in rule form, if f of x is equal to ax to the exponent n, the derivative would be n times a, so the exponent times the coefficient, and then you would leave the variable and you're going to reduce the exponent by 1. Now if the function is a constant value, then you know that the rate of change is going to be 0, so the derivative of that function is just 0. So if we reduce the tennis ball problem to a quick derivative solution, the tennis ball can be rewritten f of x is equal to 2.5 minus 4.9x squared. That was our original function. And if we take the derivative of that, 2.5, that becomes 0. Negative 4.9 times 2 is negative 9.8. And if you take the exponent and reduce it by 1, we get negative 9.8x. And if you refer back to our tennis ball problem lesson before, this was our rate of change function. So just to make sure we have it, g of x is 4x cubed plus 7, a random function that I've created. And over here, this is an approximate drawing of what it might look like. If we take the derivative of it, we're going to take 3 and multiply it by 4 to get 12. And we reduce the exponent by 1, so we get 12x squared. So here again, you can see an approximate graph of 12x squared. Now if we think about various values, we can see here that the slope is positive and very steep. So for negative x values, up here you can see that the function would be a positive value, and it's very high because it's quite steep. Then the function itself comes up here and it gets less steep. So that's why our derivative function is approaching 0. We have an instantaneous rate of change of 0. So our function is 0. And then we are increasing and getting steeper. So the derivative function is increasing. So you can see here that a cube function, if you take the derivative of it, you're going to get a quadratic function.